Good morning, everyone. It's a wonderful Tuesday morning. I have my coffee, and it's been a minute. It's been more than 10 days since the last video, so apologies about that. Gonna try to do a better job, but I do actually have a job, so I also I'm writing my thesis at the moment, which is on a Java virtual machine implementation, so um, gets a little tiring sometimes to write Rust and interpreter code. But today, we're gonna do a few things. I don't really have a plan, so we're just gonna jump into it. But I think what we definitely want to do is implement more instructions and maybe optimize a little bit in the compiler because that's always a fun little task to do. Yeah, okay, so let's get started with that. Let's see what we got. We got dup2 that we haven't implemented. So let's implement these. These are quite fun to implement. And then we're gonna look at maybe the jump instructions. No, let's start with the jump instructions. So jump instructions are really complicated to sort of build all the infrastructure for. Once they're done, it's really simple. You basically just jump the program pointer, right? Which is like the offset into the bytecode that we're looking at. So we'll have to redo this a little bit. So I think that what might be a good task for today. So the way a program counter works is that you have your array of bytecode, right? And it's just like a bunch of random numbers. Well, they're not random, they're instructions, right? But let's pretend that we don't care and know what they are. And right now we're at this instruction, okay? This is our program counter. So let's say the instruction 2 is a push instruction or something, it doesn't matter. Some instruction that just, not a jump instruction, basically. So what effectively happens is that once we've executed the instruction, the program counter advances to the next instruction, right? But if this is a push instruction, for example, of course it's pushing, and then this is the argument. For example, let's just pretend for a second that there's like variable arguments which we don't have, and of course we'd have to move the program counter even further. So the good thing about MCL is, at least at the moment, there's no variable argument size. So all arguments are 54 bits, a bit or some shit. So there's effectively no way for us to have to worry about jumping more than one program count every time. So that's why we just loop over. But remember that for in is just a loop that goes one after the other. So we're effectively going from the beginning to the end. And that's fine, unless we want to actually build any kind of software. Because if you build software and you build it without jumps, it gets very, very big. I mean, you can, right? You can just conditionally evaluate shit, maybe. I don't know. There's like ways to do some stuff, but really without conditions, without jumps, building software is very difficult. Even having no if else, that fucks it up. If you have a if else, you can do anything, but if you don't, then you're fucked up. So or goto, also good. Like if else and goto is gonna be all you need, and that's all we have actually. So in MCL at least. So I'll quit yapping as much. Let's in a second, but let's go over this really quick again. So right now we're advancing like this, and really we want to be advancing like this, but have the possibility to say, okay, this is a jump instruction, and this jumps like 4 ahead, and then we end up here, and or backwards as well. So two ways you can do that in Rust effectively. The first is that you actually have an offset, and like just literally like that, and then you start going through it. You go like, you loop, and your instruction is gonna be the bytecode at the program counter, right? And so that's how that works, right? And And that's okay. And we might do that. But then you run into the issue of, okay, I need to increment the program counter. So effectively, you would do that at the end to basically emulate the same thing. And then you would also have to check if the program counter is bigger than the length of the bytecode. Then you obviously have to break out of the loop and you're done. However, this has, like, it gets a little funny because this doesn't actually work. So if we start jumping, we have to then not do PC plus equals 1. Okay, so like we jump somewhere, we don't want to advance 1, or maybe we do, but then all our offsets are plus or minus 1, depending what we actually do. And these offsets will be hard coded into the code by the compiler. So we don't want to have to do too much math there because we do want some performance here. So if we have to do ifs all the time, I mean, this is if, and we can get rid of this later. And by just so we can get rid of this by just making sure the compiler always inserts a halt instruction at the end. So there's no real way for us to run off the end in a natural sort of code base. So we don't need this comparison because comparisons are not cheap generally, right? Because and there's multiple reasons for this we get into later in terms of optimization. But I don't want to turn this into a computer science lecture, though if you want that, let me know. I'll do some computer science lectures. Not qualified, but you know, I can yap a lot. That's a qualification. So what we're gonna do is we're gonna start with this solution and see what happens, I think, because this is the easiest way to explain why this is a bad idea. I'm not gonna hand wave, oh, this is a bad idea, let's not do this. But I do want to inform you of one other solution, which is a little funny. So assume that the program counter doesn't have to actually exist, right? Because effectively in all sorts of virtual machines and processors, you do have a program counter register that is always pointing at the memory that you're executing or some offset of something, maybe an offset from the start of the code segment or something, right? So, but you don't actually need that. You can have an entire interpreter without a program counter by taking a slice, okay? So bear with me for a second. What you can do is you can turn the bytecode into a slice. Okay, so you can say my slice is the bytecode as slice, or in a more rusty way like this. Okay, and then what effectively consider borrowing. Am I crazy? Oh, do I need to do this? Yeah. Okay, so we have a slice, and this slice is like a view on our entire data. So this is our bytecode, right? And then our slice, sorry, you'll see what I mean in a second. Our slice looks like this, okay? So right now it doesn't look any different, but we don't have a program counter anymore. Now, if we're at the position here, sorry, my cats are making funny shit sounds. Maybe not. Maybe it's just in my imagination. Maybe I'm schizophrenic. Not funny, by the way. Let's say we're looking at this instruction right here. Like this is where our program counter is, right? Remember, we started here with the program counter. Then effectively, we just have the slice looking at this, starting at this byte, okay? And so we basically built a window into our bytes of data, of code and data in this case. So just a window is a window that can slide around, okay? So, and the end of it can always be at the end because, you know, we don't really care. So instead of advancing, so of course the instruction is gonna be always slice zero, right? And so that works as well. But then at the end, when we advance the program counter, we don't actually advance the program counter, and instead we can sort of move our slice, right? So our slice becomes our slice with the first byte chopped off, okay? And so what we do by doing that is we basically chop off this first byte, and by that move the window one to the right. And we can do the same thing to move back, right? Because we have the bytecode and we can technically move this slice back if we want to jump backwards. That is a solution as well. I just wanted to let you know that that is a solution. We're gonna go with the program counter one because that's the more traditional one and the one that is honestly a little bit easier to understand and optimize for. So we're gonna do that. It's not the easiest, like it's not the best solution in general, and but we'll optimize it. So once we get into optimization, we might want to move the increment into instructions, right? We might want to do PC plus equals 1 here instead of here. Like in every single instruction, we might want to increment the program counter, because some instructions might increment it more and some might increment it less, or even decrement it, like jump instructions. So I've been yapping for a solid 11 minutes. So how about we get going with this? I mean, we did write some code, so it counts. Right now we're going to use the primitive approach, and we'll see if the what's it called, the profiler, which we're going to use later to see if our code is slow, is going to scream at us or not. But effectively, right now we don't care. So we could implement these, but we're not gonna. They're kind of boring right now. So first, let's write a program, and it's gonna become really, really obvious very quickly why we might wanna how do you say, sort of what things we need to implement. So I like to start with either the sort of interface or start with an example. And so we're going to start with an example of the usage, and then we're going to build the thing so this works. We need to come up with a new syntax here. We'll see that in a second. So we'll start with the 1 on the stack, and we're going to say, okay, I want to basically just count up. Okay, so we could do dupe. What could we do? We could do increment dupe print, right? And then increment dupe print. So this would, let's actually run this a few times without loops right now, just for fun, right? Compile exec. These are going to be easier later, of course. So okay, so let's see. We got 1, 2, 3, 4, 5. So it printed like 1, 2, 3, 4, and so on, right? So the counting did work. We did run out of bounds because our test here for the, I did actually mess this one up. It needs to be bigger or equal. But yeah, so so this is not how you write code, right? Because if you need to keep copy pasting, you're probably fucking up. So we're gonna have it once and then simply link back to it. So we're gonna have a label, which is a point you can jump to, for this, the syntax of which is gonna be a colon and then some name like hello. And then we're gonna jump to hello. Okay. So this will effectively push 1 and then keep saying increment it, duplicate it, because print will pop from the stack. So we need to duplicate the top of the stack and then print. And then we jump back to the start, increment, duplicate, print, increment, duplicate, print. So this will just count up like 1, 2, 3, 4 until eventually it runs out of integers, and we'll see what happens, I guess. But we have to implement some things here. So if I just if I run this, it will say unexpected token hello. And let's think about this. So what jump labels effectively are, and I'll like open this side by side so we can see. These are jump labels, okay? And so jump labels, I'm deciding to start them with a colon so that we can have them, like we can call one print and it's not gonna fuck with the parser because it starts with a colon. So let me drink something. So we want to basically recognize the colon character, and then everything after that, maybe including spaces. No, we're gonna not allow spaces, just like the original MCL. Anything after the colon is gonna be a label, and we're gonna use that, store basically the offset of this, like the address of this, and then every time we do jump, we basically calculate where to jump to. Now we need to look at the reference of the original MCL really quick, because we need to figure out if these have to be absolute jumps or relative jumps. So like +1, -1, or is it like jump to 5, jump to 4, and so on. Let's find out. So jump, address, or label. Jump to the specified address. Okay, so these are 2 address. So we can't say jump +2. We could implement that later, but right now we're just gonna do this. But in order to sort of simplify this process, we're gonna start without a label. We're just gonna hard code these because we can also do that. So luckily in MCL, 1 line of code is 1 instruction. So, or at least the way we're writing it. So here, this is instruction number 0, this is instruction number 1. So effectively, line number -1 is the address, right? So 1 would jump here because this is instruction 0, this is instruction 1. So this should already do what we want. And of course we can have a new line here, that doesn't matter, but I'm just doing it like this to illustrate the fact that the line numbers, or like each instruction is one instruction basically. So jump 1. Let's see if that will work. It will work. So because we did implement jump here, right? Jump, and then we implemented it as one of the ones that take a value. So you will see that the jump instruction had the value 1, which is correct. So now we need to go back to the interpreter, and let's just start with this, and then we'll build the labels later, because this is much easier right now to just get started with. So jump will do exactly one thing, that's just send the program counter to exactly what's was in the instruction, right? So instr dot pop dot oh, that's a, our op is, we want the value, right? So our value is I64. Okay. So and this is really dangerous, right? If we didn't have this check, this would be dangerous, but it's, you know, it's fine. So really we just set the program counter to that instruction's value. But we also do +=1 at the end. So there's 2 ways we could do it. We could have a like did jump true, and then, you know, if not did jump, increment the program counter. But I think the easiest way here right now is just to do the value -1 and then add it later. Or, because that's also dirty, we could do the solution where we just have the program counter increment in each instruction. No, right now let's do the -1. Be aware that this will fuck up if we jump to 0, because then we'll jump to -1, and then, you know, but it is what it is. But, you know, ooh, another solution actually that I just thought of that is maybe much easier is let's do this one actually. So next PC is gonna be PC +1, and then we just set it to that. That's much easier actually. Let's do that. I don't know why I wasn't thinking about that. So we just store the next PC. And that's gonna be it. Of course it needs to be mutable. So, okay. So this should work. This should now have the infinite loop that we want. It does. And it counts up pretty quick, as you can tell. It counts up pretty quick. It counted up to 200,000 in very little time. It counted up to 100,000 in 0.37 seconds or something. What is this? Oh yeah, 2.4 seconds. So not so bad. Okay. We know that the optimization stage, so we don't care. Okay, so this is cool. We can now jump. But again, we do want to be able to do this because then we can have new lines and we can, have more complicated programs. So let's implement that as well. And that's going to be a little bit more work. So let's see what's going to happen here. So we got the compiler. So if the raw token matches, so we need to see if we can match it. Like, can we do can we do that? Let's just use something here. Don't think we can. Yeah, don't think we can. Okay. Then we'll need to add a let's do it in here. Because this is a special case, right? So instructions are easy to parse, and then the labels will be less easy to parse. But because you can name them yourself, right? They're like variables. Sort of, you can name them yourself. So if it's an integer, go with that. Also, if it's if val starts with a colon, right? That's our label case. And our label case, let's see, so we got our interesting. So token value, we need a new token type. We need a new token that is going to be label i64. Or actually, string i64. Because we have a name and an offset, right? But we don't know what the offset is because we don't keep track of it. So we might have to redo this because we do want to know what the offset is of this label. We can obviously, we could check how many are already there, but we don't have that information because we're using .map. How can we do this? How can we do this? Could we use a different kind of iterator? That might work. Can we use that other iterator? The what's the one? We could iterate. There's an iterator that lets us like Rust iterator with Linux. There's one. Enumerate. Thank you. Okay. So like this. And so now we have the offset of the token. That only gives us the count of tokens, though. Okay, so we do have to do it as a second pass. Not a biggie. So if we encounter a label, right now we're just gonna do a token label with val 1 and 0. And of course it doesn't like that, so we just do toStrip. And Clippy is not happy. Manual strip. Oh, we can just strip count. Why not? Strip prefix. Oh, fuck's sake. Of course it doesn't work. What does strip prefix return? Option. Of course it does. Of course it does. So we know it starts with it, right? We can unwrap that safely, I think, because we do check that it starts with it here. Okay, so I also accidentally deleted the else, which is great. Oh, I didn't, it's there. Smart. Okay, so now we have a label token, and let's use that. Val parse. It's much better. Okay. Let's also use this little. Oh, that's better as well. I enabled Clippy because for some reason it was turned off. I was curious like why it was so shit before as well, but looks like the reason it was so shit is because I wasn't paying much attention to how I set up my NeoVim config. Of course it's NeoVim. Okay. Now we have these. Let's see. We're at 26 minutes. I'm thinking maybe we do the next part next time, and I'll just upload the next video like tomorrow. Just so you don't get to have to wait too long between these, because they are together. But I think we have a pretty good idea what we want. We're just gonna implement. I'll just line out really quick what we're gonna implement next time. So we're gonna say do a second pass over all the tokens, and basically we want to count the index, right? We want to keep count of maybe we do it in the compiling to the actual instruction where we convert, we keep track of which instruction we're on, we keep track of that, and we write that into the label, like, right? Because each label actually doesn't count, right? So this does not constitute an instruction. This just becomes the offset of the next instruction. So we have to do some math there, and I'm afraid it's gonna get a little bit too long to put in this episode. But I think we know what we're gonna do now. We're gonna do that, and then we're going to that should be it. Should be it. Yeah, that should be it. Do some math there. Maybe rewrite this a little bit. But I'm glad we came up with the idea of just writing it like this and not having to rewrite this map, because this map is nice. Anyways, make sure to subscribe. Thank you very much for watching. And of course, if you don't want to miss the next one, make sure to like hit the little bell, because I don't know if YouTube likes me that much at the moment. So just hit the bell and so that you get notified when I upload. I don't upload too much. I don't upload content that you don't care about. I only upload content like this and programming related content. So don't have to worry about me uploading a Minecraft Let's Play at 5 a.m. and you get notified for it. Not gonna happen. All right. Thank you very much for watching, and I'll see you in the next one, which I will upload tomorrow.